Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Networked Intelligence at the EC and RBCCPS IAC. It's my pleasure to introduce today's speaker, Professor Remco van der Hofstad. He will be speaking on who is important in a network, bringing order to centrality measures. Remco received his PhD at University of Utrecht in 1997 under the supervision of Frank den Hollander and Richard Gill. Since 2005, he's a full professor in probability at Eindhoven University of Technology. Remco was a scientific director of urandom from 2011 until 2019, and jointly with Frank, he's responsible for the random spatial structures program at urandom. He wrote some 200 papers and 3 books on random graphs, complex networks, and high-dimensional percolations. Remco is the editor-in-chief of the Network Pages, an interactive website by the networks community for everyone interested in networks. Remco is the contact person for the research area grip on complexity of the Institute for Complex Molecular Systems and the chair of the Board of Trustees of Applied Probability Trust. Over to you, Professor.
Thank you very much, and thank you for this invitation to speak here. What I'll be talking about is who is important in the network. And who is important in the network is generally measured using centrality measures, but there's tons of them. And the question is, how should we really read them? And can we bring some order into this whole vast area of centrality measures? What I'll be talking about is joint work with a former PhD student, Alessandro Garavaglia, who's now a data scientist at Gucci, George Exarchakos, who is a colleague in electrical engineering in Eindhoven, Florian Henning, who's a postdoc in Eindhoven, Nelly Litvak, a fellow professor in Eindhoven, Manish Pandey, former PhD student who's now in Aarhus, and Oliver Nagy, a former PhD student from Leiden. All right, so I'll start by saying a little bit about real-world networks and complex networks and network science in general. The whole area of complex networks has gone through a rather big boost. It started about 25 years ago when the first data sets on large-scale networks became available. And a very nice introduction to this is the book by Newman, and also Barabasi has a web book for examples and theory and a broad discussion aimed at a broad audience. Now, one of the surprises is that although networks come in very different flavors, you have social networks, information networks, technological networks, biological networks, and this list goes on, still they have unexpected commonality. And there's many unexpected commonalities. In this case, I will focus on sparsity and inhomogeneity. So sparsity means that if you look at larger networks, their average degree tends not to grow very much. And here, what we've looked at is a database of 1,200 networks in a certain database of networks. And what we're plotting here is the size of the network in a logarithmic scale versus the average degree. And what you see that there's a sort of a cloud of points, and the cloud of points is somewhat horizontal, meaning that it's in general not the case that the average degree goes up with the size of the network. So that's the sparsity. I commonly call this most networks are sparse. The second is the inhomogeneity in the network, which is captured by the fact that even though they're rare, there tend to be vertices in the network with very high degrees. That is what the inhomogeneity is. This is often called the scale-free paradigm. And here you see a plot of web crawls where you plot the log of the in-degree versus the proportion. And what you tend to see is this sort of straight line-ish clouds that taper off towards the end. Here it's for the internet. There is some sort of averaging or grouping of vertices together, which explains why this plot is a little bit straighter. And what you see is that these plots look somewhat like a straight line. Now this is a log-log plot, so here we plot the log, and there we also plot the log. And that actually means that if you look at things that are exactly a straight line, that corresponds to a probability mass function that is of this form, that pk is some constant times an inverse power of k. We've already seen this in Frank's talk. He called this the zeta distribution, but you should really think about this as being true for larger values of k. For earlier values of k, this may not be true. And this value of tau is very important. Because if tau is larger than 3 and you have a distribution like this, your random variable has finite variance. If your tau happens to be between 2 and 3, you have finite mean, but infinite variance. If your tau is in between 1 and 2, you have infinite mean. So this value of tau here really measures the number of finite moments that your distribution has. And you can imagine that, you know, a smaller value of tau will give you more variability of the large values of the degrees. And these high values of the degrees are important because if you think, for example, about the spread of epidemic, if you happen to infect one of these vertices with a very high degree, the disease is much more likely to go pandemic. Okay? So the inhomogeneity not only is surprising and is interesting to see in your network, it also plays a profound role in the network structure and the network functionality. It's called scale-free paradigm. So you're particularly asking about scale-free. So it sort of says that if you were to regroup vertices in, let's say, blocks of 5, and then look at the degree distributions of these blocks, you still see a behavior that is very similar to what we're seeing here. So somehow the scale doesn't really matter. Okay? So the general area of using mathematics or mathematical tools, mathematical concepts to study networks is called network science, and this is a science that spans sort of many different areas. Physicists are very active, computer scientists, electrical engineers, and they all have their own types of problems that they're particularly interested in. And what we generally do in this area is that we model the complex networks as a random graph, because it's so complex that deterministic rules don't really fit. So we model the complexity using randomness. And then we look at the network functionality, which is something that is sort of living on the network, and we can see that as either a stochastic process on it or an algorithm for it. So if I think of an epidemic on a network, I can think of this epidemic as basically living precisely on the network because you may spread the disease along the friendships that exist. Similarly, a computer virus will follow the cables that are in the ground that are connecting the computers. Network functionality could also, for example, be a centrality measure, and then it would be an algorithm. Right? So you basically compute a number for every vertex in the graph, and that number will tell you basically how important the vertex is. So that's more like an algorithm. And there's lots of examples that have been studied, that have been attracting tremendous amount of attention in the past. You can think about disease spread, of course, information diffusion, how the rumor spread, consensus reaching. Why is it the case, you know, if I'm more likely to have the same opinion as my neighbor, what then happens to sort of the overall consensus within the network? Synchronization, robustness to failures, what happens if vertices in the network randomly fail, or if edges in the network randomly fail. Information retrieval, that's sort of searching your information on the World Wide Web, for example. And there are many network algorithms. PageRank is an example, but also community detection. And this is a prominent part of applied mathematics, and I think that it will be remain on being a prominent part of applied mathematics for a while to come. Now, we've already seen in Frank's talk two models, Erdős Rényi random graph and the configuration model. But in fact, there's a whole jungle of models out there. I'm not going to define these models. My point is precisely that I don't need to define these models in order to prove some properties of the centrality measures that I'm interested in. Because there are so many models, you need to have tools that are very robust and that allow you to apply those tools to sort of a whole bunch of models in one go. Okay? Here I list a few static models, Erdős Rényi random graph, there's extensions which are called inhomogeneous random graphs. We've seen the configuration model. There are also things which are called exponential random graphs. There's much more. And then there's also dynamic models. We've heard somebody mention the word preferential attachment model. This is an example of a model where the network grows in time. And what I was mentioning was that we need techniques to deal with many models at once, because you don't want to reprove every property for each of these models separately. That will be a lot of work. It would be much nicer to have a tool that will actually allow you to prove this in one go. a bit like the friendship paradox that Frank was talking about. There, local convergence implies convergence of this friendship bias empirical distribution, and therefore you immediately get the convergence for free. And if you get the convergence for free, the only thing you have to do is then study what this friendship bias behaves like on limits. And that's much nicer. Okay, that was my first part. Any questions about this? Oh, I'm going the wrong way. Okay. If not, then I'll start with centrality measures. Okay. That's not so good for the people who are present online. So this is a sort of a bit of an overview. I will go in a bit more detail a little bit later. Here are three important centrality measures. The first is closeness centrality. And informally, this measures the extent to which a vertex can reach others by using few hops. Okay, so a vertex has very high closeness centrality, when from it you can go quickly to other nodes. So if you think about the spread of a rumor, this would be a very good place to start your rumor, because then it will go very quickly throughout the network. Betweenness centrality is slightly differently. It measures the extent to which vertex connects various parts of the network. Okay, so it doesn't have to have very large closeness centrality, but for example, if you have two relatively connected portions of the graph, that are then somehow connected by sort of more loosely connected vertices. These loosely connected vertices are very important because they occur as a bridge to, for example, spread an epidemic from one side of the network to the other side of the network, and therefore they're important. So we already see that there are different notions of importance. This is important in one sense, this is important in a slightly other sense. And PageRank is it measures the extent to which a vertex is visited by a very specific random walk, sometimes called the board surfer, and it used to be used by Google to rank the importance in web pages. So three different centrality measures. Okay, good. So the very first one is degree centrality. Okay, you can think of a node being very central when it has many neighbors, or when it has sort of many in-neighbors. Okay, and we've already seen this picture. I'm just showing it again. It really is the very simplest example of a centrality measure. In fact, you only need to know to whom you're connected in order to be able to compute this. Okay. PageRank is slightly different. I was mentioning that this is related to random walks. And in it, you have a certain damping factor, C, or a restart probability 1 minus C. And then P denotes the normal random walk transition probability on the graph. So this is the conditional probability of being at I and then jumping to J. And this is related to the out degree of my vertex I. I basically follow each of its out edges with equal probability. Okay? And in terms of this P, the PageRank distribution satisfies this recursive equation. And the way how you can think about this is that at any moment of time, my Markov chain on my graph with probability C will follow one of the edges in the graph and perform a normal random walk step. And with probability 1 minus C, it will just forget about everything and just restart at a uniform location. So this is what we call a board surfer, because you can think about you sitting behind your laptop, sort of following the links on the web page, and then at a certain moment you're bored and you start doing something completely different. Okay? Now, this is a stationary distribution, and therefore it sums up to 1. But my networks are going to be very, very, very large. So if you have something that sums up to 1 in the network, on average, all the values are going to be tiny. Okay? That's not so nice if you want to take a limit. So instead, what we do is we blow it up by a factor n, so that in fact, on average, this number will become 1. So we call this the graph normalized PageRank. And this is useful because we want to take a large graph limit, just like Frank was doing for his friendship bias. And in this case, this PageRank vector, which of course depends on your graph, for any graph of size n, will satisfy that if I take a vertex uniformly at random, the average value of its PageRank will just be 1. So now I have something to compare it to. If the PageRank would be much, much larger than 1, you know that it's quite large. If it's very, very, very small, much smaller than 1, then you know that it's actually relatively small. So now you know compare your centrality measure to. So closeness centrality, how do you measure that? So I look at the closeness centrality of a vertex V. I take the number of vertices minus 1, and I divide that through by the sum over all other vertices, the distance between the two vertices. That's for simplicity, just assume that the graph is connected, so that all of these numbers are actually strictly finite. And that will give you your closeness centrality. Okay? And again, it's the case that if the centrality measure is large, you think of the person, of the node as being important. And this is closely related to what is called the Kevin Bacon game. I don't know whether you've heard of this. In the Internet Movie Database, people were trying to connect, let's say, various actors through collaborations in movies to Kevin Bacon. Being close to almost everybody is then actually quite handy. And somewhat related to harmonic centrality, which you get by instead of taking 1 over the ratio, taking the sum of 1 over the distances. And you may expect that actually these behave in a very similar way. Betweenness centrality does something similar, somewhat related in any case. And here what you do is you measure the extent to which the vertex of interest, which is denoted by V, is along shortest paths or not. Of course, there could be many shortest paths here between my vertex I and my vertex J, and then sigma ijv is the number of shortest paths that will pass through V, and the sigma ij will be the total number of shortest paths. Okay, so if a large proportion of shortest paths between, let's say, all pairs of vertices in your network pass through V, then it has high betweenness centrality. It's important for somehow information traveling between different parts of the network. Now, one of the problems is that this is computationally quite heavy because you need to compute how many paths there are between I and J, and then how many of them actually pass through V for every vertex, for every pair of vertices I and J. So this is a bit of a problem if you really want to do this on a large network. That becomes almost infeasible. And related is load centrality. Let me not go into that. And there's many other related centralities. These are more related to, let's say, matrix properties, eigenvector centrality, cut centrality. So we have many centrality measures. And it's not entirely clear how to even think about them and how to even, for example, show that two centrality measures behave relatively similarly on a large body of networks. And that's actually what this talk is about. I'll be thinking about a connected, undirected graph or a strongly connected graph. That means that all of these centrality measures are well defined. And I will first say a little bit more about PageRank and discuss what is happening when the graph becomes very big for PageRank on the graph. And then I will study how to compare centrality measures in the real world. Okay, large graph limits. Okay, so recall that this was what PageRank was. And PageRank actually is a very important centrality measure. It's used all the time. It was invented by Google. They wrote a paper bringing order to the web. I call my talk Bringing Order to Centrality Measures. There's a bit of a pun there. The whole structure of PageRank, due to its recursion relation, is that PageRank is large for vertices that have many important vertices pointing to it. But of course, this is a bit of a recursive definition because it's not going to tell you who's important. But basically, you can solve this by solving a matrix equation, a matrix recursion. And to me, this at least seems highly appropriate to classify the importance of networks. If there's many important people pointing to me, then probably I'm important too. If there's many important web pages pointing to a certain web page, I would be more likely to think that that web page is important too. Now also, there's much empirical data that suggests that if you look at the proportion of vertices in a network that have large PageRank, so this, you should think of this X as being quite large, that also obeys a power law. Okay? So there's, again, huge variability in the PageRank per vertex if you look across the network over the different vertices. And that could actually be a reason why PageRank behaves rather nicely. So here are two pictures for this. Here we see again sort of a log-log plot for citation counts. That's a citation network. You look at a collection of papers, and you look at who refers to who. And that gives a directed age along a citation. And what you see here is that this is the graph normalized PageRank, and this is the citation distribution, so that's the in degree in your network. And what you see is that these seem to be following straight lines, and the straight lines are horizontal. And the slope of the line in such a setting really is, oh, I never know what this is doing. I just wanted to go back, but never mind. These power law exponents turn out to be the same. Maybe I should just do it here. Much better. Yes. Okay. Yeah. So this is sometimes called the power law hypothesis. So the power law hypothesis says that the power law exponent of the in degree in your network very often is the same as the power law exponent of PageRank in the same network. Okay? So this is a hypothesis. We don't know whether it's true, but of course we can test it for different models. And for different models, we can show that it's true rather generally. It's true for directed configuration models. It's true for directed generalized random graphs. And in fact, it's true for almost all undirected graphs. That's actually very nice. So this is very promising. But there is also an example for which the power law hypothesis is not true. That turns out to be directed preferential attachment models. So in preferential attachment models, it's a dynamic model. Vertices come in one by one. A vertex comes in and attaches to a vertex, let's say, proportionally to the degree of that vertex. Now you can think of this as being a directed edge directed from the young vertex to the old vertex. And if you view your graph as a directed graph in this way, it turns out that PageRank has a heavier tail than the in degree. Quite interesting. So sometimes it's true, sometimes it's not. The reason why it's true for most undirected random graphs is that you can prove that in undirected graphs, connected, PageRank is always bounded from above by the degree. And therefore, if this satisfies a power law, this cannot satisfy a heavier power law. Okay, this gives a one-sided bound, but it turns out that in many of the models you can actually turn that into a two-sided bound. Yeah, if I press the same button, sometimes it goes forward and sometimes it goes backward. I don't understand what it's doing. This is working fine. Okay. Okay, this is where I was. Let's see whether this does work. Okay, so that's very nice. And that sort of tells us that indeed the power law hypothesis is often true, though not always. And we don't really know when it is true and when it is not true. So that remains to me a fascinating question. It is n times that. Yeah. Yeah. Not quite, because of the uniform restart. So that has a different stationary distribution, namely the uniform distribution, but it makes it less strange that indeed they have the same power law exponents. Okay. Now we've already seen in Frank's talk that a tool in network science or in random graphs is to look at local convergence. And it turns out that PageRank actually behaves relatively well under local convergence, in the sense that if you have a sequence of random graphs that converges locally, the PageRank distribution will converge along. That's a very nice property, because then it means that you only have to look at PageRank on infinite graphs in order to study, for example, the power law behavior. And this is true very generally. Now, bear in mind that in the example that Frank was giving, he was looking at friendship biases. And for that, it's sufficient to know all the vertices at distance 2, at distance 1 and at distance 2. So you only need to look at the 2 neighborhood of a vertex in order to compute the friendship paradox. That's not enough here. So here it will slowly decay if you go further and further, but it will never stop. Okay? So it is local, but you do have to go quite far. So the statement says that if Gn converges locally weakly, then there exists a limiting distribution which has mean less than or equal to 1. We don't know whether it is 1, such that the PageRank of a uniform vertex in your graph will converge in distribution to the PageRank of the limit. And if you have the stronger notion of convergence locally in probability, then there exists a limiting distribution, same properties, such that for every continuity point of this limiting distribution, you actually get that the proportion of vertices whose PageRank is strictly larger than R converges to this limiting probability. So PageRank behaves well under local convergence. That's quite nice. Now, here I didn't say anything about what local convergence is. I have a few slides on this. So local convergence has been proved for many sparse random graph models. Basically all the ones that I was mentioning before, it has been proved. Some of these local limits are very easy. Frank gave 2 examples for Erdős-Rényi and the configuration model. Some of these local limits are actually quite complicated, like for the preferential attachment model. And local convergence has all sorts of very direct implications. So it gives a one-sided law of large numbers for the the proportion of vertices in the largest connected component. It gives, or is basically equivalent to convergence of the proportion of neighborhoods of specific shapes. So if you look at a vertex and ask, you know, what does its 4 neighborhood look like, and for which proportion of vertices does this 4 neighborhood look like something very specific, then that will converge, either in distribution or in probability. And you have convergence of various other functionals. This is a very lively area of modern probability. And even if you're interested in a property that is not quite local, often local convergence gives a very good starting point. Okay, so for example, if you're interested in graph distances, obviously not a local quantity because, you know, graph distances tend to grow logarithmically or something like that. But still, you could sort of start exploring locally until your neighborhood is very large, and then hopefully, because if you're, hopefully, when your neighborhood is very large, you get some concentration and you can more easily compute the path length between sort of sets of very large sets of vertices. So often it gives a very good starting point for an analysis, which is quite nice. Okay, let me see. Yeah, so maybe I'll say a little bit more than Frank about this, because I find it actually a beautiful theory. It takes some time to digest, I realize that. So what I start with is a graph, any graph. It has a vertex set and an edge set, and now I root it at a point. Bear in mind that was also what I was doing in the previous example. I was looking at the PageRank at a specific node. So I'm looking at the graph from this particular node. But then, of course, I need to know what this node is, so I'm just going to add this to my graph, and now this gives me a rooted graph. It gives me a point from which I can look at the graph. And from that point, I can then look at neighborhoods. So, you know, what is the subgraph of vertices that are at distance at most r? So that's a nicely defined, rooted subgraph of my graph, rooted at exactly the same point. It's going to be a finite graph because my initial graph is finite. And therefore I can see, you know, if I have 2 of such graphs, rooted graphs, are they the same? Well, they might have entirely different vertex labels, so you can't really say that the graphs are the same. Right? There should be somehow a mapping on the vertices that will map the one graph into the other. And that's an isomorphism. So I have a rooted graph, and they are isomorphic when there exists a bijection from the vertex set of the one to the vertex set of the other, such that the root is mapped to the root. You should have the same point of perspective, and an edge will be mapped to an edge. So that actually means that in my bijection, if I map an edge on both sides with my bijection to the other side, that should also be an edge, and that should be if and only if. Then basically these graphs are the same. And then we can put a metric on this. So I call this to be 1 over 1 plus r star, and this r star is the largest value for which these r neighborhoods are the same. Okay? So if r star is infinity, they're actually isomorphic up to every distance, and then I call these graphs to be the same. Okay? It turns out that this is a nice space. So you take this space of rooted graphs, modulo these isomorphisms, because two graphs that are isomorphic we call the same. And then this is a well-defined Polish space under this metric. Okay, and what do we then do? Well, we start looking at continuous, bounded continuous functions, and we look at the expectation of such bounded continuous function with respect to a random root. So I take a root chosen uniformly at random, and then I look at the expectation of this randomly rooted graph. And what I want is that this converges to some limit. Okay, so this is the traditional sense of weak convergence of random variables on a space. You start with a bounded continuous function, and the expectation of that will converge. Now there's a slightly stronger notion, which is local convergence in probability, and there we want this convergence not just in terms of the expectation, but even conditionally on the random graph. And then, of course, this is going to be a random variable. It's exactly this random variable, and we want that to converge in probability to the same limit. That is what local convergence is. All right. So how do we then prove that PageRank indeed is local? Well, we sort of have this commuting diagram. We want to show that the PageRank at a uniform point converges in distribution to some limit. But doing this directly is a bit difficult, because this is about stationary distributions of Markov chains on graphs that actually tend to infinity. Not entirely trivial how you should do that. However, what we can do is we can approximate this PageRank by basically the PageRank sort of, it's an iteration of a matrix. We can just truncate that iteration. That will give us a finite sum, and that is what this beast is. Okay? Since I only perform the matrix multiplication capital N times, my capital N here is fixed, this actually is a deterministic functional of my N neighborhood. So it's local. And therefore, by local convergence, this will immediately converge to exactly the same thing for the limit, which also only looks at distance N. And if I then know that this one actually converges as capital N tends to infinity to this limit, I actually get this commuting diagram, and I get my result. That's exactly how it works. What you need to know is some uniformity in how well this is being approximated by that. And that turns out to be exponential in capital N, with a factor something like 1 minus c to the raised to the power capital N. Okay. Any questions about this? Yeah. So the small n is the size of my graph, which I'm taking to infinity. And the capital N here is basically my finite neighborhood approximation to PageRank. That's what it boils down to. Any other questions?
First down arrow, what is at the bottom left?
This one? Okay. Let me go back. Let's see whether this, Okay, good. Yes, here we go. Yeah, here. So we can think of this as a matrix relation. And we can iterate that relation. Okay? And this is a constant here. Okay, so whenever we hit one of these, we're going to get something relatively simple. And if we don't get this, we're basically iterating our P matrix. So do that iteration capital N times. And then replace this R by, I think, 1. That will give you a pointwise upper bound of your recursion. And that's what this capital Rn is. And since you only apply this matrix P, which is the random walk transition matrix, capital N times, it means that it's only going to get contributions of vertices at distance at most capital N, and therefore it's going to be local. Okay? And since this convergence, if you apply this matrix iteration many times, is exponential, the thing that you've thrown away is actually exponentially small. That's why it works. Exponentially small in capital N in the number of iterations. All right. Good. So the last 10 or 15 minutes, I would like to address the comparison between different centralities. So why would we want to compare different centralities? There could be many reasons. So I was already mentioning that betweenness centrality is computationally quite heavy. So maybe there's some other centrality that basically ranks the vertices in a very similar way that would be computationally less heavy. Okay? Then you don't have to do all of these computations, compute betweenness centrality exactly, and maybe you can live with the approximation. But how do you even compare centrality measures? When do you say that two centrality measures are very similar? That's a non-trivial question. And in the literature, this has been investigated. And people, for example, use a correlation between different centrality measures. Now, I would argue that this is not a good measure. And the reason is that I'm not actually so much interested in the precise value of my centrality measure. I'm interested in relative values. So that actually means that, if I apply a monotone function to a centrality measure, I actually get exactly the same centrality measure. But applying a monotone function and then computing the correlation, you could basically get anything. Okay? So correlation works well if you apply linear functions, but not if you apply other functions. Okay? So if you're interested in the ranking, correlation is not the right thing. Also, you could argue that we're often very much interested in the most highly ranked vertices. So the vertices with very high centrality measure, which is only going to be a very small proportion of your network. And maybe you just want to see whether they are alike. Okay? So not only do you want to say two centrality measures are very similar, but maybe you also want to be able to say, well, if I just look at the first 5% of the vertices that are most highly ranked, these sets are very similar. Okay? So how do you do that? Well, we invented something which is called the Centrality Comparison Curve. And I have to go through this, and I know I have to do this slowly. So again, I'm here with a graph that could be directed or undirected. And I have a centrality measure on it. In fact, I have two centrality measures on it. And what you should think about is that we're trying to compare these two centrality measures. So I have centrality measure R and I have centrality measure S. What I would like to do is take the intersection of the, let's say, k most highly ranked vertices and divide that through by n. If that would be very close to k times n, then actually these two sets are exactly the same, and then I know precisely that they have the same top k ranked vertices. Now, one of the problems in some of these centrality measures is that they may have the same value. So, for example, if I take a centrality measure, the in degree, I may have thousands of vertices that have degree 2 and degree 3. So it's a bit difficult to compare them. How should I do that? You could then, of course, randomly order them, but then, you may be thinking that two centrality measures are very different because they're being tossed around in a slightly different way, but still their initial values were the same. Okay? So what this does is it tries to do this in the best possible way. So it tries to match the two centrality measures as best as it can. So how do you do that? Well, if I have two vertices, I'm going to be introducing a total ordering. So I have to say when a vertex A is strictly smaller than a vertex B. And for every two vertices, I want to be able to make this distinction whether A is smaller than B or B is smaller than A. So I say that A is smaller than B for these two vertices when it has smaller centrality value. Now that's very clear. Okay, it's going to be a total order basically prescribed by the centrality measure. But of course, it could be that they actually have the same centrality measure, and then I still want to be able to order them. Okay, and I want to order them in such a way that sort of the two centrality measures are as close as possible. So I'm going to also say that A is smaller than B when the R values are the same, but the S values are ordered. Okay? Well, but it could be that there's still vertices for which both the R values and the S values are the same, and then I'm just going to do it randomly. Okay, so that's my three-step procedure. This will indeed, for every pair of centrality measures, give me a total order on the vertices, which is basically induced by the pair of centrality measures, where clearly R plays a much more important role here than S, because S is basically only used to break ties. And the uniform values are also only used to break ties. Okay? So if your centrality measure would be such that it only takes on different values, then you really order according to R itself. Okay, and now I'm going to define a curve, which is a curve from the unit interval to, let's say, fractions over n, so numbers 1 up to n divided by n, by looking at the x times n most highly ranked vertices in this ordering and in the reverse ordering, where the role in S and R has been interchanged. So this you should think of as being the x times n most highly ranked vertices in the one, and these are the most highly ranked vertices in the other, and I take the intersection. And then I divide that through by n to make it a number in between 0 and 1. So if this number would basically be x, these two sets would be exactly the same, and then it means that these two centrality measures at least put these two sets exactly the same. So if I take for x k over n, then it represents the overlap of the k most central vertices according to R and S. Okay?
Use the same U values for both of these?
That's a good question.
Resample or keep them the same?
We keep them the same. Yeah. Yeah, good question. Okay, so I'm trying to tell you that this is a useful object, and that this might bring order to this whole jungle of centrality measures that we have out there. There are literally hundreds of centrality measures. So for that, I'll first have to tell you how to read such a centrality comparison curve. So as I mentioned, okay, not sure. Yeah. So this is a curve that is monotone in x, and actually when it's equal to x, you know, the two centrality measures should be very similar. Okay? So that's what this says. It's always less than or equal to x, and it should be roughly equal to x, which is the diagonal curve, when the two centrality measures are similar. However, I mean, very small x means the highly ranked vertices. So it could also be that you have two curves that are very close to each other for small values of x. Okay, then the centrality measures as a whole, on the whole range, may be different, but at least they have similar most highly ranked vertices. That could still be very relevant, depending on what you want with your centrality measures. Now there's another side to it, and that is when the two centrality measures are independent. So for example, you could also just randomly order your vertices, give them labels 1 up to n in a random fashion. Then what is going to happen to your centrality curve? Well, the two centralities are going to have nothing to do with each other. And then it turns out that the centrality curve is basically x squared. Okay, so that's the parabola. Also, you could have maximally different centralities. So for example, instead of taking R, take the opposite of R. So the maximum value of R minus the value at V. Okay, these sort of swap the two sets around completely. Maximally different. And then this curve is roughly 0 to x minus 1. So this is a line that starts at a half x at 0 and then goes to 1 all the way up. Okay, it has to end at 1 because if I take all the vertices, the intersection of the two sets is going to be n, because all the vertices are in this top set. So that's the way how you should be reading the pictures. Okay. So this is high energy physics archive. The vertices are pages or are papers, and it's a directed set. So you look at the citations, and you follow them. We do these two computations. Here we see in degree versus PageRank. They're not exactly the same, but they're not too far from a straight line. So in degree and PageRank seem to be sort of ranking these vertices in a similar way. That may actually be related to the parallel hypothesis. Okay? And the same for CUTS versus PageRank. And betweenness and closeness centrality, well, it really starts deviating rather significantly more from the identity curve. So you could say that these really are quite different. This is the Stanford web graph. And here, you know, in degree and PageRank do not look so much alike. And here even, it seems that betweenness and closeness centrality, at least initially, seem to be close to being independent. So this would say that in terms of the most highly ranked vertices, closeness and betweenness behave completely differently. Which is an interesting statement, if you think about it. Okay, here we have in degree versus out degree, in degree versus PageRank, and betweenness 10 versus in degree. This is a very big network, so we can't compute betweenness centrality on this network, but this is an approximation to betweenness centrality with sort of only looking at vertices that are at distance at most 10. Okay, so computationally that one is easier. All right, and now we're doing it here for the directed configuration model. I want to particularly point at this paper. This does the finite distance approximation to betweenness up to distance 6. And this does it for the full betweenness. Here we can actually compute that. And what you see that it's relatively close to a straight line. So remarkably, in the configuration model, in the directed configuration model, you can quite well approximate betweenness centrality by betweenness centrality just based on distance 6 shortest paths. It's an interesting concept. And this is in degree versus PageRank. At least initially they seem similar. That's consistent with what we know about the parallel hypothesis. And here we do betweenness versus closeness for the directed configuration model. This really is very close to x squared. Okay? So this gives you at least a visual way to compare how similarly centrality measures rank the vertices in your network. Conclusions. Well, we have several plots for PageRank with different damping factors. So that's the constants little c that I was talking about. And it's fairly insensitive to it. So it doesn't really matter how you pick your C, you're going to get very similar rankings based on PageRank. Closest centrality is virtually identical to harmonic centrality. It was a slightly different ratio that we were computing, but you hardly see that back when you compare the centrality measures. In degree often is quite similar to PageRank, though not always. Out degree certainly is rather different from PageRank. And in some cases you see that in and out degree are completely independent. And this is important in terms of sort of local convergence type properties for centrality measures. The computationally heavy betweenness centrality and closeness centrality you can approximate rather well by their local versions, which is also a nice property computationally. So we believe that this centrality comparison curve is a useful addition to network science toolbox, and it brings some order to centrality measures. There's many open questions here. Show that it behaves well on the graph limits. That is ongoing with Manish. And do a large-scale clustering analysis of the centralities using CCC. So, for example, do a clustering analysis for this body of 1,200 networks that I was using initially to show that most networks are sparse, and see which centrality measures behave alike and which don't. That's going to be a much more applied project. So I think it would be very interesting to do this. Oh. The next one is the last slide. Yes, conclusions. Yeah, so I've tried to argue that networks are useful to interpret real-world phenomena. Think about centrality measures. Frank was talking about friendship paradox. There's unexpected commonality between networks. I discussed the scale-free phenomenon that we see in many networks, but also many networks turn out to be small worlds. So that's something that is common throughout network science. And we use random graph models to explain properties of the network. And then, of course, it is an important question whether then your conclusions are universal. So if I have a conclusion for the configuration model and I draw a completely different conclusion for the preferential attachment model when the degrees are similar, which one should I trust? That would not be a good thing. And what you would like to have is that conclusions that you draw in one model should be mirrored in another model. That's not always the case, but sometimes it is. And in many cases, we have not seen, but it is true that these local limits often have branching process structure. And that's actually some universal feature between many of the models that have been studied in network science. Thank you very much.
We'll take some questions.
Thank you. I have a couple of questions. So
Yep.
one is complexity-wise, there's not much of a gain from moving from betweenness to closeness or to PageRank for large networks, right? So betweenness would be order number of nodes times vertices. And then
No, betweenness is much more, because you would have to do this for every pair of, for every
Right.
vertex, you have to compute all the paths that pass
Right.
through your vertex,
this is weighted or unweighted?
unweighted.
Yeah, so the Brandeis algorithm is order nm, right?
But will it also compute the number of paths?
Yeah,
Also through a vertex?
through the vertex, yeah.
Ah, okay. That I didn't know. Thank you.
So it's similar to the closeness because you'll have to
Uh-huh.
run Dijkstra's. So
Yes.
the savings would be similar, right? In terms of moving from one centrality to another.
PageRank I would still believe to converge more quickly, because its iterations converge exponentially. So it's really sparse matrix multiplication, and that is quicker than between a centrality.
Yep.
And we certainly see this in our computations, which we've done through network X. Closeness really is much slower than, betweenness really is much slower than closeness in practice.
Yeah.
So for our large patent network, we were not able to compute betweenness. We were able to compute closeness. So there really is a difference in practice.
Right. And did you make any comparisons with a sampling-based approach for betweenness? There
No,
are a
that we
few
didn't do.
papers. Okay.
No.
And this all of these are unweighted.
Yeah, these are all unweighted. Even though you could do very similar things for weighted
Weighted.
networks. I mean, that's not a big problem. You could also compute the centrality. When your centrality measures are local, then I would believe that also the centrality comparison curve will converge to a deterministic curve in the limit. So that's what we're working on. Now, many of these centrality measures are not local. Closeness is not local. Betweenness is not local either. Now, one of the things that we're also thinking about is proving limit theorems in the dense setting. And in the dense setting, betweenness and closeness behave much nicer. So we're hoping that in the dense setting, we may be able to prove large graph limits there as well. We see in our pictures that if we do simulations, all these CCC curves, they concentrate very well for all the random graph models that we've computed them for. So there's much nicer behavior than what we can prove.
I meant local in this sense. Like, for example, here, across the entire network, you're trying to identify the nodes with the highest centralities.
Yeah.
And then that's what you're trying to ensure
Yeah.
happens with this other centrality measure too, right? So that's how
Yes.
you're comparing these centralities.
Right.
So, but let's say you take one particular node or vertex, right? And from its point of view, you rank all its neighbors according to one centrality measure. and we want to.
But how do you rank all the neighbors? Oh, all the neighbors.
Let's say we take the
I see.
PageRank.
Yes.
Let's say we take PageRank.
Yeah.
And we have vertex I.
Yeah.
Among all its neighbors, we want to rank the PageRank of its neighbors.
That's a very natural question. We have not thought about this. For PageRank, we know that all the PageRanks in your local neighborhood will converge. That's the local convergence result. So you could do this. And you could do it for another, I mean, if you have a local centrality measure, you could do it for that one as well. And then you know that they actually simultaneously converge. And then it becomes a problem of the local limit. But it's still a problem of the local limit. So it may depend on the precise structure of your local limit.
Okay.
How, I don't know. It's a nice question. Thank you.
You observed in many of your plots at the end that integree and PageRank matched very well, but not out degrees. Is there also a theorem to this effect for some random graph models?
So you could interpret the parallel hypothesis in this respect, in the sense that they both have a similar parallel behavior. However, it's not entirely the case that then also the most highly ranked vertices are the same. Because you can have high PageRank in many different ways. You can have a high PageRank when you have many neighbors, and they all give you a little bit. You could also have a high PageRank when you have one neighbor that has excessively high PageRank, and it will give some to you. For example, because it doesn't have very many out edges. Lots of in edges, but few out edges. Then you're going to profit. So it's not entirely the case that the collection of vertices, that the parallel hypothesis implies that also the collection of vertices that PageRank finds the most relevant are also the same one as for integrate.
So universality is all over the place. How does that exactly combine with your centrality measures? So do you see in your comparison of your centrality measures also some form of universality? I mean, the question is a bit vague.
Let me give you a counterexample. So for PageRank, we actually know that for directed configuration models, etc., the parallel hypothesis will always be true. But if you orient your edges from young to old, it's no longer true. Okay, so that I would call a non-universality result.
Okay, but that then comes from the orientation, where you could say
that comes from
I'm really looking in some sense at a different network. Well, okay. But do you see in other cases sort of streaks in your whole ordering? I mean, you were talking about maybe I should order my centrality measures in groups of similar things. Do you see some form of universality in there, or is this not?
Yeah, so we have tons of pictures, dozens of pictures, and we were trying to see sort of by eyeballing, see sort of a clustering pattern emerge. It's not always so clear. I mean, sometimes in and out degree behave similarly. It depends a little bit either on your model or on the precise real-world network on which you're computing it. Sometimes they behave completely differently. So I'm still hoping that there might be some sort of a clustering where you could say, well, you know, in broad strokes, these two centrality measures very often do the same thing. Closeness versus harmonic centrality is an example. And there's also betweenness and a slightly related version that is a betweenness-like similarity measure. They also almost always behave very similarly.
Yeah, great talk firstly. But I just had a small doubt. When you're comparing measures of centrality, some naive ones have a tendency to not give a complete ordering over all the vertices.
Yes, precisely.
Versus some more sophisticated ones will give you like a small fraction so that you can actually rank them properly. So wouldn't you run into problems when you're taking your CCC curve and then?
Well, I mean, we didn't come up with this total ordering for nothing.
But
so the total ordering is really trying to make the centrality measures as close as possible.
Right.
I mean, we also looked at random ordering. So, for example, we would immediately use this rule. So S would not play a role. But then you somehow see that you can have strange effects that are just coming from the randomness. I'm not interested in that randomness, that's just totally artificial.
But let's say you're taking an integree or something of
Yeah.
that sort. It's very likely that a lot of
Yeah,
nodes
precisely.
will have.
So you're going to have many vertices for which there is a tie.
Right.
And this breaks the tie in the way for which the CCC curves will be closest.
So do you want to essentially compare two measures which have similar, or let's say one gives only integers versus one gives real numbers? Would that be a fair comparison of sorts, or?
Yeah, that makes no difference. I mean, we can multiply our centrality measures with everything.
Okay.
I mean, by pi, and then all of a sudden they take completely different values. We're only interested in the ordering that they produce.
Okay.
That is an important point. So if I take a centrality measure and take e to the power it, it's still exactly the same ordering. And to me, that's totally fair, because I'm interested in, is a vertex more highly ranked than another vertex? That would just say that its centrality should be larger than the other one. If I apply a monotone transformation, that's still going to be the same. So you have to find a way to compare centrality measures that obeys this sort of monotonicity principle.
Right.
So that's why we came up with this.
Right. Thank you.
Yeah, so if there are no more questions, let's conclude this session. Thank you, Professor.
Thank you.
Thank you, Remco.